1, so I know HU and SL would be equal to 0.5. In this case, I'm not really concerned with how difficult it is to manufacture. I know I need to leave some amount of tolerance on my hole. I can't give it a 0 on both sides, so I'll just set them both to 0.25. And I know that I can get away with that in my design. So this is a bit where you can see the difference between your straight math class where you're solving for the one solution that would work and an engineering case where you're using some of your intuition, some of your judgment and your experience, or some really good analysis if you don't have that experience to figure out what will work in your situation. And keep everything on the plate here. Does everybody follow that? Okay, good. I know it's not the most fascinating topic again, but it's a very useful skill to have, even in some of your assemblies. So I think about, like on the ISBVI team, on the Braille e-reader, you have a lot of pieces that are going together. You're mass producing a lot of small pieces to make one device, right? And you want to know for sure that as you assemble those, each of them work correctly. This is the way to do that analysis and figure out how this would be. So like I said, this is a very simple geometric way of doing this. There are a lot of different solutions that would have satisfied these equations, but I'm going to use some judgment to get there. You can do statistical processing. So if you're going to make 100 million parts, you may be willing to accept that there's a possibility of some of them not working, but the probability is really low, and I can open my tolerance to accept more parts if I have a low probability. Okay? So there are some more complicated ways to go about doing this, but this is kind of a basic, straightforward, no-nonsense way. Everybody follow that? Okay, except for that guy right there. He didn't follow it. Okay. So you say, but I'm an electrical engineer. I don't do anything like that. Well, you do, right? So if you're an electrical engineer, you create PCB schematics, things like that, you're going to end up with a very similarly looking part. You're going to have a layout. It may have dimensions on it. So this would be fabrication of a PCB for a production, a big manufacturing level design. So this isn't specific just to MEs. It's definitely applicable to most branches of engineering. If you're not an engineer, which some of you certainly are not, you still need to know how to use these things because you'll communicate with people. So when I was, again, in orthopedics, we had a lot of people who were from marketing backgrounds that would be on technical sales or support for the field, and people would call in and say, something isn't working, I don't understand something, and they had to go back to the prints and read to understand what was happening. Okay? So it's not a skill only for engineers. Oh. Yes? No? Master builder, you have to learn how to read prints, okay? But prints are really just the beginning, okay? There's still a lot more to do from the point where you've specified a print, all right? That's not the end of production. That's the beginning, right? So the next thing would be to make the part, and there are a lot of ways of doing that. Starting with creating your CAM model, right? So you went through, you did your design in CAD, you created a print, now you need to go and build your CAM. That manufacturing router that we talked about. So you may have a machine CAM for making one particular piece of the part, but there may be several steps to making that part. So you need the router and then the bill of materials. So a lot of different things there. One common problem with undergraduates who do design work and build prototypes is they think everything is made in one of these. And that's not the case in industry. Okay. So how many of you own products that were made by a 3D printer that you didn't make yourself? Yeah, one? Okay. How many has something on them right now that was 3D printed? One? Two? A couple, right? How many of those are your prototypes for EPICS? All of you? Yeah, okay. So very uncommon to get production parts from a 3D printer, right? It's starting to be more common, but this is not how most things are made. So you need to learn to think beyond the simplest way to make the part and think about how are you going to make more of these. This is a more common way to do that, all right? So this is a mill. And there are a number of different ways to make physical things, right? There are things like casting, which is a way of forming metal by putting it into a mold or a shape, okay? There's molding, which is very similar, but usually for plastic, right? So you're going to do like an injection mold like the Legos we saw at the beginning, okay? There's machining, so that's a subtractive way of making things. So a mill like this one, you're going to take a tool and you're going to cut material out. There's stamping. This is a lot of like the shells of a car are made, right? So you want to get that shape, or how they used to be made back when they were metal. there are things like forging. So forging is basically smashing hot metal into a shape. Traditional way of thinking of that is the anvil and forge. That's not really the way they're done these days. It's a lot more elegant than that. And then there's some joining things like welding or brazing. This is where you're getting things hot and attaching them together. You could do epoxy. There are a lot of different ways to make parts, okay? There's no way we could cover even close to what all of these things are in any detail here, but be aware there are mass production level ways to make a lot of parts. So I'll show you a quick example of a really nice CNC operation just because I think this one's kind of cool. Or no, I won't. Perfect. You can make a guitar. It's cool. And then finally, after you've made the part, you need to check the part, right? So you've had someone make these parts. You need to verify that they're all correct. They'll start with your risk analysis. This is something that you all should be doing. Should be done toward the beginning of a project, not toward the end, contrary to popular belief. And then you would update it as you go through the project, okay? So you're going to go out front and look for how could my product go wrong? What are the things that could happen along the way? And try and mitigate those early rather than waiting till the end to check. The other side of that is testing. So as you've done risk analysis up front early on, you're going to identify what are the things I need to do to verify and validate that my design works. Okay? Verification is checking that you've met your specifications. We talked about at the beginning. Validation is checking to make sure you met your user needs. So I could verify that this table can support 300 pounds by putting a weight and doing a test on it. And then I could validate that it works for working on a car by setting a car on it and working on the car, right? So that would be use versus sort of a function test, right? So if you're in software, you could think about verification would be a unit test of one function in your software, where validation would be setting the user down and having them go through and use it and make sure that it really works. Inspection happens in a lot of different ways. You can have simple tools like these, a measuring tape or a caliper, and that all depends on what those tolerances you set are, okay? If you set your tolerance in, say, a 1/16 of an inch or greater, you use a tape measure, no problem. If you have a smaller tolerance, say in the the thousandths of an inch, right, or tenths of a millimeter, you would want to use a caliper like this or even smaller micrometer. Or if you want to get into something that has more detail, you could use something like this. So this is a CMM. It takes basically dot points all over a surface, and it can generate a very fine point cloud, so you can look at a complex shape. Or you could do some of this 3D surface scanning like this. So there are commercial things like white light scanners that create a surface like this. You can check that against an original model to see how far you've drifted from a surface that you intended. Okay, so you can get into some very detailed ways of checking parts. Another good way to check parts is by using gauges. So that's where you create basically a functional mate that has all of those tightest tolerance requirements you have and checking to make sure that your part will function with that. So within all of this, there are a lot of different engineering roles, and I alluded to this at the beginning. So not all of you are engineers, but a lot of you are. So we all think of the design engineers, and all the things we talked about, really your responsibility is to get to prints, okay? So all of those design activities you do, especially if you're in the mechanical field, so if you're writing code, this is a little bit different. But if you're making a mechanical thing, a physical thing, all of your effort, all of that human-centered design process you did, going out building empathy, meeting with customers, iterating through conceptual design, culminates in a boring print, okay? A piece of paper with drawings on it and dimensions, numbers, okay? But that's how you control the creation of something amazing that you did through this whole design cycle. So while it's a boring thing in practice, it's an amazing thing what it can do for you by taking all that work that you did and producing something physical and real, okay? If you're a manufacturing engineer, which a lot more of you will end up being than you think, you'll do things like figuring out the tooling for making the part. You'll figure out the machine programs for creating those things. You'll create operator training. That's sexy, right? Teach people how to do something. But that's how you get a part made the right way so that you can get it out in the field. You might be creating those routers and bills of material. And then there are quality engineers, and they're the ones that are responsible for helping you check parts. So they'll design those gauges. They'll help you come up with criteria for your part to say, what is it that you're analyzing in your part? What are the really important dimensions and which ones aren't as important so that you can make that part in a cost-effective way, okay? Because there's usually a lot of different ways to manufacture a particular feature in a part. Some of them are expensive and some are cheap. The expensive ones usually give you really tight tolerances. The cheap ones usually give you really broad ones. So you have to figure out what do you really need. They'll help with things like a first article layout. So this is where you do a first manufacturing run, and you check every detail of those parts and make sure that they're what you want before you ramp up into a full production. Okay? So again, this is just a kind of a big survey level of what you might encounter in industry as an engineer. I'm going to skip most of this part just to save you time, but some things to be aware of. Design for assembly is designing so that the part can be put together in the simplest way possible. Okay? So you may try and minimize your part count. You try and make interfaces so that you can't mess them up, right? So if you think about, you have a part where you could insert one side or the other side, and it'll go into your assembly either way, but one is right and one is wrong. Better to design that so you can only put it in the right way. Okay? Some of those types of things, you try and eliminate those mistake opportunities. So another good example of that is if you're doing an assembly that uses a bunch of bolts. If you can use all the same size bolt, then the assembly person just grabs a bolt and puts it in. If you use a bunch of different sizes, they have to sort through them, pick out the right one, more opportunity for error, right? So that's design for assembly. Design for manufacture is when you actually optimize the part itself. So you're trying to design the part to be easy to make, all right? So a great example of all of this would be this little design here. This one comes from Georgia Tech. So an engineer originally designed this little toolbox with two separate sides that are held together with nut and a washer and a lock washer and the handle. Much simpler design. So they had 24 parts that went into this thing, 8 different types of parts, a lot of different procedures to get this made for a very simple geometry. Much better design was the second one where you created the whole thing in one bending process and then you just snap the handle in, right? So you can imagine the amount of time it takes you to assemble that piece versus that piece. The amount of mistake opportunities there are here versus there. So this is where, as you get through, you've thought about how this should work for your user. You want to dig a little bit deeper into your design to say, how can I make it so that we can fabricate this thing easily and cost effective? So on a similar note, costs in design. So this is the little bit I'll give you about costs. As you go through the design process, so you start out with a problem. You could have an infinite solution space, right? There's a lot of different ways you could solve the problem. The costs are really undefined at that point. What's going to cost you in the end? But as you start to get into the conceptual design phase, you've accounted for most of the cost of this. So if you look at the phase of product life, so if you can't read these very well, this is conceptual design, detailed design, testing, process planning, production. And then this is the cost of the product, so this is 100% of the end cost. You actually incur pretty little cost doing conceptual design, right? You're talking with customers, you're doing prototype development. It doesn't cost very much. But as you get into production, those costs go through the roof, right? That's your actual spend. But the committed cost, what this thing will cost you in the end, is almost completely defined by your design in the beginning, right? So if you get through your design, you figured out your solution, and you go to your manufacturing people and you say, now let's figure out how to do this in a cost-effective way, it's too late, right? Those costs have already been specified by the design choices you made all along the way. So you really want to think about those things up front. So for a lot of years now, a lot of industry has been practicing concurrent design. So the old-fashioned way was design engineer makes product, makes for that prototype, says, here, manufacturing engineer, make this for me. Concurrent design is the idea that you have those manufacturing quality people with you from the beginning to say, okay, here's the problem we're going to solve. Here are the ideas I have. And say, well, this one would be cost effective, this won't. This decision is good, this one is bad, from the beginning, so that you can head those things off up here instead of committing all this cost. Okay? Everybody follow that? So work with your broader group. And that's why most of your teams are multidisciplinary. We try and get you different viewpoints so that you can help understand all of these things early on in the process rather than getting stuck at the end. Okay? So I will let you skip the exercise because we're about out of time anyway, but if you're really interested in doing tolerance analysis, I'd be happy to help you one-on-one. I won't make all of you suffer through doing tolerance stack-up homework, although it would be helpful for you to do it. Okay? Any questions? No? All right. Have a good day.